What's up, and welcome to Surging Ahead. This is Brett, and today we're going to talk about Andrej Karpathy's most recent talk at the CVPR conference on full self-driving and what they're doing to convert to vision only. This should be an interesting conversation, so stick around and we'll dive right in. So we're going to go over this presentation, and I'll pull out some parts that were exciting to me. I've got a couple video clips and a few slides that I snapshotted out of it. But if you find this at all interesting, I highly recommend that you watch the whole thing. It's a little under 40 minutes, and it's a very good talk. He goes into a lot of detail around several items that I'm not going to bring up, but I think there's value in those, so I highly recommend you watch it. And the link for that video will be right here. I also have it in my YouTube description, full clickable link. Okay, so now we'll go ahead and pull up the first video excerpt I have here, which is talking about some of the weaknesses in radar and how vision only helps them to address that.
Now, when radar has a good lock on the car in front of you, it's given incredibly good depth and velocity. But the problem with radar is, like, once in a while, at random, it will give you a dumb measurement, and you will not know when that is. And so it's incredibly hard to fuse with vision in our experience. So it might suddenly see a spurious stationary object because of a manhole or because of a bridge, or crossing objects are not very well tracked, or oncoming objects are not very well tracked. And it ends up contributing noise. I'll go into more detail in a bit. But for our purposes, what we want to do right now is we want to match the quality of these predictions using vision alone. So the question is, how can you get a neural net to predict depth, velocity, acceleration directly and do it with a very high fidelity, matching that of radar? So the approach we're going to take, of course, is we're going to treat this as a supervised learning problem, and we need a massive data set of depth, velocity, acceleration on a lot of cars, and we're going to train a large enough neural network and do a very good job at that. That's the standard vanilla approach, and that actually works really well if you do it properly. So here's what it took.
So there were some interesting things in there, and he also talked a little bit earlier about some parts on some of the difficulties with radar, in that it is also sort of an issue for them because when they're dealing with radar and when they're trying to figure out the worth of it, they have to dedicate a lot of people to trying to solve those problems. And so he mentions that radar at this point, for vision, I guess, and as opposed to radar, vision is quickly approaching 100x more accurate than radar. And in order to work on these problems and to use radar, they have to have a radar team, which right now they say they have about 20 employees working on these neural nets. So they have to have a team to work on radar, and then they also have to have a team to work on radar vision fusion. So if you're taking 20 employees and say the teams are only 2 people, that's still 4 people if you do the radar team and a sensor fusion team, right? 2 each, and then you're leaving 16. That's like, what? 20% of your employees are then forced to work on these 2 sensors, which are 100x less accurate. I can understand the economics of not wanting to dedicate that and to try to do that, especially when it's quickly becoming less and less valuable. So yeah, those were his thoughts around that. Okay, he then goes on to talk about triggers, and they currently have 221 triggers to bring up information to help them bring back data to improve the neural net. And the slide shows several of the ones they use. One of the biggest ones is just the shadow mode, which is out there at all times in the background, tracking information using the newest neural nets. And when it pulls information that is different from what either the standard neural nets use or then the driver would do on those things when they disengage, then it will send back information. They also will do specialty cases on edge cases they know are an issue and they want to try to solve. So they'll use specific triggers in that case to say, hey, this event happened. Now we need to take this information and send it back. But here's just a screenshot of several of the ones they use out of what they currently have of 221 triggers to track information and discrepancies. So moving on from the triggers, he then goes on to talk about shadow mode and exactly how that's working and what data they're getting back and how they're using that to improve the neural nets. So we'll go ahead and watch a quick excerpt of his talk on that.
So basically, over the last 4 months, we've done quite extensive data engine. We've ended up doing 7 shadow modes and 7 loops around this data engine here, where on the top right is where you begin. You have some seed data set. You train your neural network on your data set, and you deploy the neural network in the customer cars in shadow mode. And the network is silently making predictions. And then you have to have some mechanisms for sourcing inaccuracies of the neural net. So you're just looking at its predictions. And then you're using one of these triggers, like I described. You're getting these scenarios where the network is probably misbehaving. Some of those clips end up going to unit tests to make sure that even if we're failing right now, we make sure we pass later. And in addition, those examples are being auto-labeled and incorporated into a training set. And then as a asynchronous process, we're also always data cleaning the current training set. And so we spin this loop over and over again until the network basically becomes incredibly good. So in total, we've done 7 rounds of shadow mode.
So all of that shadow mode data produces this final data set, which is quite impressive. They basically said that over 4 months, they were able to run 7 rounds of the shadow mode, which totaled 1 million 10-second videos, with 6 billion objects labeled and accurate depth and velocity data on it, which totaled 1.5 petabytes worth of data in total they used to feed those shadow nets, which this just shows the scale at which Tesla is able to operate because of their fleet. When almost all of your fleet is collecting this data and sending it back to you, you're able to identify edge cases, use those to build your network and do it fast. And I don't think any other manufacturer is able to get this much data this quickly and feed it back in. It's very impressive. He then proceeds to talk about the neural network architecture that they're using to analyze this data. And so we'll bring up a quick clip of that.
There's basically the layout of the synthetic visual cortex in order to efficiently process this information. So our architecture roughly looks like this. We have these images coming from multiple cameras on the top. All of them are processed by an image extractor, like a backbone, like think ResNet kind of style. Then there's a multicam fusion that fuses the information from all the 8 views. And this is a kind of a transformer that we use to fuse this information. And then we fuse information first across all the cameras and then across all of time. And that is also done either by a transformer, by a recurrent neural network, or just by 3-dimensional convolutions. We've experimented with a lot of kind of fusion strategies here to get this to work really well. And then what we have afterwards, after the fusion is done, is we have this branching structure that doesn't just consist of heads, but actually we've expanded this over the last year or so, where you now have heads that branch into trunks that branch into terminals. So there's a lot of branching structure. And the reason you want this branching structure is because there's a huge amount of outputs that you're interested in, and you can't afford to have a single neural network for every one of the individual outputs. You have to, of course, amortize the forward pass for efficient inference at this time. And so there's a lot of feature sharing here. The other nice benefit of the branching structure is that it decouples at the terminals, it decouples all these signals. So if I'm someone working on velocity for a particular object type or something like that, I have a small piece of neural network that I can actually fine tune without touching any of the other signals.
So there's a lot interesting in there. And it's a really high level approach to what they're doing. But I think possibly the biggest revelation there and what they're talking about is that they are, in fact, with the vision, finally truly incorporating that data over time structure to analyze things, which should greatly help with pathing and take care of a lot of the problems we're seeing now. Now, with all this data, they do need to figure out a way to store all this. 1.5 petabytes is not a small amount of data. And then beyond that, they need to be able to work with that data and do various things with it to understand and label and track and feed it back into neural nets and have that not take years and years and years. So what Tesla has done is create this supercomputer, which there's some photos of it and kind of telling how big it is. He went on to say that Tesla believes this is the 5th largest supercomputer in the world. And this isn't even incorporating Project Dojo, which hopefully we'll get more information on soon because they believe that to be crucial in getting to the next steps of full self-driving. So, yeah, a very neat looking computer. Okay, so continuing on, we have I talk about how they were able to start seeing strong reduction in phantom braking. So we'll go ahead and pull up that video here where he talks about that.
Here's another example, fairly infamous example of slowdowns when there are cars going below a bridge. The issue here again is that the radar does not have too much vertical resolution. So radar reports a stationary object in front of you. It's as if like the radar doesn't know that there's like a stationary car in front of you or if it's the bridge above. It cannot differentiate those two. So radar thinks that there might be something stationary in front, and it's just like looking for something in vision to tell it that it might be correct. And then we create a stationary target and brake. And so in this case, in the legacy vision predictions, which were already producing depth and velocity, but because we were using radar, the vision inaccuracies were being masked because your bar is only at radar association. Your bar is not at actual driving. And so the depth and velocity were not held up to a high enough bar. And so basically what happens is vision reports for a few frames, reports a slightly too negative velocity for the car. And then it associates to the stationary object. And the stack is like, oh, that must be the stationary thing. And then we brake. And so this, of course, is much cleaner. And you see that the new stack does not see this at all. And there's no slowdowns in this case. Because we just get the correct depth and velocity, and vision obviously has the vertical resolution to differentiate a bridge from a car and whether or not the car is slowing or not.
Okay, so here is a quick video in which Andrej goes into the reconstruction and depth mapping and what that looks like with the vision-only approach. I just find this kind of interesting, so I thought I'd share this quick little excerpt with you here.
So here we see a clip, and this is a vision-only estimate of the depths of all the points. And of course, you don't actually want to really deploy these measurements directly into a car because they are too raw. So what you actually want to do is you want to, again, auto-label. And you want to really think about what is the information I really need at test time in the car? And what is like as close as possible to action, right? So you want to do all this work at training time, figure out exactly what happened in the clip, reconstruct the entire environment. And then you want to actually like post-process the curb at training time. So you want to do as much at training time and labeling time as possible. And then you want to figure out what are the tasks I really need at test time. And that's the thing that happens in the car, subject to very strict latency requirements. You want to do as little post-processing there as possible.
Okay, so that pretty much wraps up the presentation. There were a couple of questions from the audience that Andrej took. The first being around automating triggers to find new categories that they need to send data back on. And Andrej just said that, at least at this point, that's too difficult. And while it's an interesting idea, it's not something they're really digging into at the moment. And then the other question that came up was around sensors, such as continuing to use radar for situations like bouncing the image under cars to see vehicles in front of them that are stopping. And to which Andrej just replied, there are a lot of sensors out there. And all of them have their own value, but there's also a cost associated with all of these, and whether that be an economic cost from the actual price of the items to the human cost of developing them. At this point, they see the most value in really concentrating on vision and fully doubling down on that sensor to try to get to autonomy, because they think that sensor by itself essentially can accomplish everything they need to have a full self-driving vehicle. So that was their stance on it, and that pretty much wraps up the presentation. And there's a lot that I found interesting here. It was nice to see what Tesla is doing to try to advance their vision-only software suite. It shows a lot of the reasoning behind what they think they need there, and it shows the advancements they've made and the progress they've made just over the last several months. And it's nice to see that it is solving some of the problems. It also appears to be introducing some others, which they didn't really speak to here, but you see some reports of issues maybe driving in the rain, maybe it restricting speed earlier than the radar versions of cars would in that, the requirement to have your auto headlights on and them freaking out a little bit while driving on the interstate and stuff like that to try to make vision able to see better in the dark. And just some other things like that. But hopefully those are just growing pains, and as they continue to iterate on this suite, they see massive progress very quickly. Okay, thanks for watching this video. This has been Brett from Surging Ahead. Let me know what you thought of this video. If you thought I got it right, if you thought I got it wrong, have any differing opinions or any thoughts on where you think this is all headed, please leave a comment in my comment section. If you liked this video, go ahead and hit the like button. And if you want to see more videos from me in the future, hit that subscribe button. Well, once again, thanks for watching. This has been Brett from Surging Ahead. Have a great day.